only do that, right? So I don't have a deep knowledge of the subject, and just use this techniques for our own purposes, but I cannot qualify myself as a very deep, say, expert on machine learning. But this is useful for the next talk that I will deliver tomorrow, and this will be on scientific machine learning. So I need to go through this basic notations and basic concepts. So I hope this will be useful to some of you. You already seen yesterday this picture. So artificial intelligence is a big field where you can put so many different things, but in particular, from the mathematical perspective, what is important is that, at least to me, what actually characterizes artificial intelligence from a mathematical perspective is the possibility of machines to learn autonomously without being programmed for doing it. And in particular, the artificial neural networks are not the only algorithms that enable machine to learn, but are very likely the most popular and successful algorithms today for machine learning. And then as you go deeper and deeper, you find other realization of artificial neural networks, in particular the deep neural networks and the large language models, like those that are at the basis of the, say, text generation or image generation, like GPT or others. So this is the picture. So I'm putting myself here today in the machine learning stuff, and then I'll go to the artificial neural network specifics of algorithms. And again, please free to ask questions during the exposition. So what is artificial intelligence? Well, this would deserve hours, but there are many definitions. Actually, there has been the first definition, which has been evolving in time. The first definition was actually the very first one was not a definition, but it was kind of a conceptual setting. This was due to Alan Turing, but it was not under the formal definition. This is the 1950. And the very first formal definition is from John McCarthy, 1955, for the Dartmouth conference that took place a year later. And McCarthy said that the artificial intelligence is the science and the engineering that make machines intelligent. And machines meant basically computers at that time. Okay. So this is from 1955. So this definition has been evolving a lot during the years because the subject itself has been evolving a lot with the many different achievements and very, disappointing events. So there's been really a very oscillatory trajectory. And in the 70s, Larry Tesler basically came up with this definition, which is not actually a mathematical definition. He said AI is whatever hasn't been done yet. And what did he mean by this? Well, people were so confident in the development of the field that they thought that if something was not yet solved or addressed, it would have been addressed later on thanks to the artificial intelligence. So it basically gave artificial intelligence an immense power, ideally, to address and solve any possible problem. And this is called sometimes the AI effect in the literature. There have been several other definitions in the following years, and here I'm just reporting 4 of them from different sources, as you see. Marvin Minsky is one of the say collaborators of McCarthy. Is one of the co-organizers of the Dartmouth conference in 1956. And here is the definition. It's a much, gave it much later. Say, the science of making machines to do things that would require intelligence done by man. And again, you see all those definitions depend on intelligence, and intelligence, you cannot find a single definition of intelligence. You cannot even find a single definition of machine. So trying to get machine and intelligent on the same line is a bit, is a kind of challenge, say. Now, if you look at the Oxford Dictionary, so the capacity of computers or other machines to exhibit or simulate intelligent behavior. And the European Commission in 2019 stated that artificial intelligence refers to systems that display intelligent behavior by analyzing their environment and taking actions with some degree of autonomy to achieve specific goals. And I think this is good. See, I mean, you really have to say that this is driven by a goal. And this is sometimes called the restricted form of artificial intelligence, comparable, I mean, it contrasted with the so-called general artificial intelligence, according to which artificial intelligence should be able to say machines should be able to behave as human beings. This is the so-called AGI, general artificial intelligence, and we're not yet there, right? We're only, I mean, what we experience today is the weak artificial intelligence of strict artificial intelligence, restricted artificial intelligence, the one that is capable of solving specific goals and not with, say, any aim of generality. There is also another concept, another definition of artificial intelligence is the super intelligence, right? The super intelligence is the capability of being even more intelligent than humans. So it's a kind of dream, and I guess that we all hope that we'll never be there. So we're very far from there today. So today we can only say that we are on the weak artificial intelligence domain. So, and then let me also add this one, which is not a definition, but is the very first one that was given, this very first statement that was somehow reported in the original paper by Alan Turing. And I guess that some of you know that Alan Turing reported in 1950 with this very famous paper, a test for the machines to become to be judged as intelligent. And basically the Turing test works as follows. You have one human being who asks questions, and then in another room, which is separated by walls, say the coffee room here, you have two other entities. One is another human being, and another one is a computer. And this person here asks questions, and the other two answers. And the interrogator states that the machine over there is intelligent when he is no longer able to discriminate between the answers, whether it's given by the machine or by the system, right? And this is encoded into this statement by Alan Turing in his paper. AI is the set of abilities demonstrated by hardware and software systems that, in the eyes of a human observer, the interrogator in this case, might appear to be exclusive to human intelligence. All right, so this is, roughly speaking, the scenario. So you see, there's not a single definition, it's not a mathematical definition, but we basically all agree that it has to see with the behavior of machines to say to the attitude of machines to behave as if they were human beings. So it's a vague definition, but I think that we can understand what we're talking about, right? Good. So it's a story that started 70 years ago, more or less. And why has it become so important in the last years, in these years? Well, basically for three factors, I would say. The first one is data, big data. The second one is big computers. And the third one is algorithms, right? Big data because you need actually many data to train the artificial neural network that we'll see in a little while. And you need big supercomputers because you want them to, as we'll see, to solve minimization problems in very high dimensional spaces. And then you need big supercomputers. And then you need suitable algorithms to allow supercomputers to treat those data. So this is the trinomium. I don't know if you know, can say it this way, that enabled artificial intelligence to become so important, so popular in these days, I would say. So big data, how big is big? Here is a picture where we report the estimated number of data available worldwide. So some computer scientists started counting the data available worldwide in the web, basically. And that since we are mathematicians, we believe that all the knowledge of the universe can be encoded into data, right? Pictures, videos, and every kind of information. So counting the data is somehow a way to count the knowledge of the universe. You can extrapolate a little bit of the concept. Right? So they started in the mid-80s, and they estimated this number here in terms of data, and then and this is the curve, and this become, say, more and more important. And of course, you don't have to go to the single figures, but there are two elements here that are quite striking. And the first one is that the first element is that we estimate this data to be 175 zettabyte next year. And what is a zettabyte? It's easy to remember because this is the 21st century, so a zettabyte is 10 to the power 21. So this is the century of the zettabyte, right? And what is a zettabyte? I mean, it's a big number, of course, but how big is big? Again, well, assume that you sit down calmly on your chair and you look at a video, say an HD video, high resolution video, and you be there for 36 million years. And this is one zettabyte. So the content of a video that lasts for 36 million years is the number of byte is one zettabyte. Just to give you the idea of what we're talking about here. But there is another element which is very striking, is the rate of growth. And you can see that, roughly speaking, every 18 months, you double the number of bytes. Which means that, I mean, if you take this day, today, if you look back to the history of humankind, I mean, the knowledge that has been accumulated until now will be double in a year and a half. So this is the pace, right? And so what do you do with all this data? We try to use them. And basically, we try to use them to, in the machine learning, environment. And then you have supercomputers, you need computers. And I think you know what is the actual power of supercomputers, but this is the biggest supercomputer available today is Frontier. And it's capable of carrying out 1.6 billion operations per second. What is 1.6 billion operator per second? 1.6 10 to the power 18. So you have 8 billion people on Earth, and you ask each of them to perform 200 million operations per second. So this is the power of this supercomputer. Right? Of course, not all the training of neural networks is carried out on the Frontier, but this gives you a bit the idea of the actual trend.
Actually, we can add that Google just ordered the first 4 nuclear reactors for their data center.
Yeah, this has to see with the issue of the sustainability. The point is that, as far as I know, the big data centers are in the United States. They used to be located in the desert. Now they are located in areas with a lot of water, like in the western part, Virginia. And indeed, now they started realizing that the water is no longer enough. So they've been draining all the water in the ground. So this is why, one of the big thinker of this era, I will not say the name, but who I'm talking about, recently said that they need to reopen the 3 Mile Island nuclear central to feed that, to cool down the supercomputers. So it's, I mean, that's a big issue. I was talking yesterday about the sustainability of just solving 1 second of heartbeat, and here, of course, you are facing an incredible challenge. So machine learning, there are basically we can classify the task in 3 different families, I would say. Remember that this is the ability of machines to learn. without being programmed for that. Right? The first is what can be called discriminative for data classification, data categorization. See example. Second one is generative, like the large language models, like ChatGPT say, and this is for data generation or text generation or image generation. And the third one is reward aggregation, what we can call reward maximization. So those are the three main, I would say, families of interest or applications. Say. Now, if you look, for instance, the first one, the categorization, and we have data, you want to understand what is behind those data. If there is a law behind those data, for instance. So the goal is to construct what can be called a mathematical classifier that assigns a label to a given data point. So you have points, distribution of points, and you want to classify them, basically giving labels. We'll see an example. And the classifier can be linear or nonlinear. For instance, artificial neural network are nonlinear classifiers. And here, from the mathematical perspective, there are two different kind of approaches, I would say. The first one is what can be called statistical learning. And in this case, the training data set is generated by a prescribed probability distribution. And here, the most important issues from the mathematical perspective are to characterize, that's a very bad word, the learnability of the algorithm in terms of the training set size. How much can we learn from a given data set? Right? And the second one is the computational complexity. How can we estimate the computational complexity of defining learning problems? So these are two big issues, and there is some theory, but it's a very say incomplete theory in this respect. The other approach is online learning. This is even more difficult. In this case, you have a continuous stream of training data. For instance, if you are working on markets or sensors, social media, you continuously feed your training set, you increase the number of data available, and the learning models, so the algorithms are updated as soon as new data become available. All right, so there is a connection with the game theory from a mathematical perspective, but this is that's a very hot topic, say, the online learning. And you want to change continuously, increase continuously the amount of data that you have, and that will be used to learn. Okay, so I gave first some definitions of artificial intelligence, and now we are talking about machine learning. So here again, we have several definitions. And I'm just quoting among the very many definitions, very few of them. So the first one is probably due to Arthur Samuel. Arthur Samuel in 1959, or first of all, Samuel is the one that created the first checkers program with an IBM computer. And this was back in 1959. And this was so shocking at that time that the IBM share increased overnight by 15 points. The first time people could realize that you could use computers that were used for different purposes to do something completely unexpected, like playing games, say. So Samuel, the definition of Samuel is this one. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed to do that. Okay? And much later, 2017, among many other definitions, I picked up this one from the Royal Society. Machine learning is a set of rules that allow systems to learn directly from examples, data, and experience. And that's very important. So there is no theory. You learn from experience, from data. Okay? So there's no theory. There's no background theory here. And then I'd like to give the last one, the one that is probably the most, how to say, deeper, or the deepest in my understanding, is this one. So these two guys are two professors in Berkeley, two statisticians, actually. Michael Jordan, it's the same name of the famous basket player, but he's a mathematician, and Tom Mitchell. And they say learning is the process of transforming information into expertise or knowledge. So you have information and you have to derive knowledge. Say. And machine learning is automated learning. So it's an automatic way, automated way to go from data, from information into knowledge, say. And the same Tom Mitchell proposed a statement, which is, I believe, very important and very useful. He said a computer program is said to learn from experience. So you see core names here in highlighted three different terms here that are important. So a computer program is said to learn from experience. Experience will mean data, basically, availability of data. With respect to some task P, you should have a task accomplished, and some performance measure P. If its performance on T on the task measured by P improves with experience. So roughly speaking, the more data you have, the more experience you have, in principle, you should be more capable of the computer should be more capable to learn. And the way it learns is measured by performance measure P. So that's the idea, okay? And indeed, you can try to fit all what you are looking at to project the whole thing onto this simple statement and try to identify the experience, the P and the E for the different tasks, say. And here is my preferred task. How do you recognize, how do you ask a computer to recognize a picture of a dog or of a cat or whatever, say. So, and my analogy is this one. If you have a small kid or a small grandchild and he doesn't know anything about life, but you take him or her to the say to the park, and you want to teach him or her what is a dog. What can you do? You when you see a dog, you do bow, right? And you do it 2 or 3 or 4 or 10 times or 15 times, depending upon the kid, until when next time you meet a dog and you say wow himself. And then you'll understand that he understood what is dog, right? So there's no fear. I mean, you're not telling the kid, you know, a dog is an animal with 4 legs and a tail, and so no fear, no knowledge, no background knowledge, but just experience. So what is the experience in this case is the 10 times that you met a dog and you say wow, right? This is the experience. What is the outcome? Well, is the learnability of the kid. So it's when he is able from that point on to identify a dog by himself or by us, right? So here we have a picture. So now you want to tell a computer how to recognize a dog. And of course, you cannot take the computer to the park, right? So you just give him, sorry, it, a certain number of pictures. And those pictures are pictures of dogs, cats, trees, houses, whatever. And this is supervised learning. So it means that you yourself put 1, instead of saying bow, right? You put 1 to the picture that are representing the dog and 0 to the other pictures. Then the computer, this is the experience. So you collect a training set of data, right? So and those are, so you have n pictures, you have n pictures and n labels, 0 and 1 in this case. Then you have to define a model, a mathematical model, which is a function that will be in principle able to represent this distribution, say, and then you have a new picture, and if the model is good enough, when you have this new picture, the computer itself should be able to go from that picture X to its label 0, 1. Okay, so you have a performance measure, and the performance measure in this case is that you define a, say, a cost function. Cost function is the sum of the errors or the discrepancies that your model is making when it analyzes the given data set, plus perhaps regularization. And you optimize this, namely you minimize this loss function with respect to the parameters. And those parameters are those that the model should learn. So the model should learn those parameters. if you know if it does learn those parameters, then the model will be completely set. And then from that point on, you can use this model to analyze new pictures. That's the idea. Okay. So you have a task, recognizing a dog. You have an experience, which is a set of data. You have a performance measure, and then you are back to the, say, the previous setting here in this specific example. So. And this is supervised learning because we have been, when we define the training set, we have been labeling the pictures. This is another example, another task. You want to predict house prices, Y, based on X, and X is a set of information. For instance, you have square footage and the number of bedrooms, the number of bathrooms, and so on and so forth. Of course, such a function, transfer function from X to Y, does not exist necessarily because the price of the house may depend on many other factors, many other elements. For instance, where is the house? If it's in Paris or it's in the middle of France, say. But you try to predict this input-output function in a reasonable way, say. So you collect a set of training data, again, several houses and corresponding prices. In this case, you just look for a linear regression. So you don't have necessarily to look for artificial neural networks. So the model could be a model artificial regression. Then again, you have the loss function, and which defines a performance measure. And of course, again, you need to use an optimization algorithm. In this case, this is very easy, this part, because you have the nonlinear, the normal equations. So you do it by hands, basically, right? And you end up with a linear system. In the case of neural network, this is a different story. So in the second case of the regression, L is quadratic. So you have to look at you have a single, say, minimum. So you compute the gradient and you end up with a very simple linear system. So this is the easy part. But if you have a neural network, this is another story. The experience, I've said before, the experience is, say, consists of the number of training set. And here you may have different approaches. You have the supervised learning, the one that I've been talking about before. We help the machine to identify the answer on the training set, right? So we put the label, the example before. You may have the unsupervised learning. You just give the machine photos, and you don't tell them that they are photos of cats or dogs, right? So it's completely blind. Or you have the reinforcement learning. In this case, the training set is not given a priori. It changes dynamically, like when you have a continuous flux of information or of data from the market, for instance, from the social media. And there is another actually example, which is called semi-supervised learning. And this I found it very important. And I'd like to make an example. If you go to a hospital and you go into, say, a radiology department, they may have, I don't know, thousands of exams or magnetic resonance or CT scan of the brain, if they deal about, say, tumor in the brain, and they may have thousands of those, and only a few of them have been analyzed by the doctors. And analyzed means that the doctor has basically diagnosed this, identified, is it tumor, is not a tumor, and if it is a tumor, which kind of tumor. So they have 1,000 data in the training set, and only 10 or 20 that have been labeled. But in this case, the supervised algorithms are so good that they can take advantage also of the other, say, 990 that are not supervised. This is a very classical situation in some environment, like, for instance, in the clinical setting. So those are the three main approaches when we talk about training set and the experience part. The task, what can you do with machine learning? Which kind of problem would you like to solve? Well, regression, you want to predict a, say, function that is good enough in approximating the distribution of data. This is something that we encounter very, very often. The second one is classification, which is used for images, like in the case of the dog, or stand filter. You want to identify whether or not, to decide whether or not, say, an email message is relevant for you or not. Right? So this is artificial intelligence, machine learning, or for detections. This is supervised learning, but you have then unsupervised learning, like clustering. You want to split a set of items into subsets by finding similarities or differences. You find economics in biology, social sciences, associations for recommendation system. You want to discover the probability of the occurrence of items in a collection. For instance, you want to recommend get a message and they recommend us to buy a certain book because they basically understood that we like that specific author, or we like the subject, or just because in the past few months have been opening websites that were talking about that specific subject, right? And so on and so forth. So there are many, many different type of tasks that you can face. A performance measure. Well, how do you select the loss function? Basically, you need a distance between the predicted value of the model and the actual value of the training set, and this can average the errors that you are making. You can use mean square error, you can use mean square error, root mean square error, and you have other more sophisticated, say, performance measures. Now, since we have a distribution of data and we created a model, and I'm not really yet talking about the model, I'll do it in a while. Of course, the issue is which kind of error are we going to make? And here, please remember that we are not in the presence of an exact solution that we know. Maybe we do not know explicitly, but we know that this should be the exact solution of a certain PDE, and we are approximating it. It's not a matter of approximating an exact solution, which does exist with an approximate, say, solution. Here we have a distribution of data, and you don't even know if there is a single function that goes from the input to the output, but you want somehow to construct such function. And when you construct such function, you like to predict the error that you made, basically, a certain kind of error. So the goal is to find a function f hat from a finite set of samples. So we are in a space that we can call yx, and x and y are the input and target spaces. Input pictures, target space, the label, for instance, or more sophisticated text. So yx is the set of functions from x to y. Assume that you have a probability distribution on the Cartesian product of x cross y. You have a distance which measures the mismatch. So this is the loss function, for instance, and you have the expected risk. The expected risk can be defined as R of f. R risk is the integral over x cross y of the distances between y and f of x. So x is any input data. F of x is what your model predicts, and y is the truth, the ground truth, say. And this integral is the expected risk. We are actually looking for a subspace where you look for your model function. And we have a training set. This is called the hypothesis space, this H subspace. We have a training set, and we have an approximation of this expected risk. This is an integral, and you want to approximate it by, say, a suitable way, a numerical approximation of the integral. And in particular, you can define Rsn as being 1 over n, the sum over all training set of the distance between yi and f of x. So the prediction of the model and the ground truth. And this is called the empirical risk. And it depends on the training set. Because to approximate this integral here, we are just using the training set, the functions in the training set, or the elements in the training set. So the function that it depends on what problem makes it. They are features, those will be features. So this is the setting.
I guess that you can put a square, which would be in the definition of D. D is not a distance, it is a loss function. So it could be a square.
A square of this square, you mean this square?
A square of a distance.
You can put the square of the distance set. Well,
and you can put, I think, a weight on the I in the empirical risk.
There is no probability.
right here?
Yes. You could put a rho I.
You mean a coefficient?
Yeah.
A weight function. Oh yeah, this is very general.
Yeah. That would go to the definition of the probability.
Okay, right.
We assume that the probability equidistributed.
It's equidistributed, yes. Yeah. So ideally, you would like to find the projection of f hat, which is the ideal input-output function onto the subspace. So f hat in this case will be the arg mean of R of f for all the function f in y of x. In fact, you are approximating R by RSN by numerical integration. So what you're looking for in practice is this function here. But it's not even there because you have to minimize the loss function. And then you minimize the loss function, you will not be able to minimize it exactly. So we stop your algorithm given time. So what you're actually looking is something that you can go ahead and start HS. So in principle, if you want to measure, if you have an idea of the error, you can try to find the discrepancy between R of f hat, empirical risk, minus R of f hat star HS. And by triangle inequality, if you cannot do better, you can have, say, the sum of three different kinds of errors. The first error is basically the approximation error. How well you approximate your space by the hypothesis space. And this is the error that you have in a Galerkin approximation, say. The second one is the difference between the exact integral and the numerical integral. And this has to see with the so-called generalization error. How well the training set represents the input and output spaces, because remember that this quantity here is an approximation of the integral based only on the original training set. Then we have an extra term, which is this one, and this is due to the optimization error, called optimization theory, how well the optimization algorithms work. And finally, we have RSN minus R of the final solution. And this is bounded by the uniform generalization error. And generalization error is, again, the one that tells you how well your training set is capable of representing the whole distribution of data set. So in principle, if you can analyze these different terms, you will be able to get an estimate. And I think that we are very far from having a complete theory in this respect, meaning a satisfactory estimation of all those terms, all those errors. So this is very general. It's for any possible model, say, but which kind of models are actually used for machine learning? Remember, models is the construction of the function f that connects new data to new outputs. And here you can have linear models. Remember that in all cases you have coefficients that you have to determine by the minimization of the loss function. Polynomial models or decision trees or random forests. Those are classical statistical approaches. And several others, like maximal merging classifier, in case you want to separate data. For instance, those are, this is the R2 space, and you have data that are associated, for instance, to a positive value and other that are associated to a negative value. You want to separate them in a linear way or a nonlinear way, or there are support vector machines where you rewrite the maximal classifier, or you have artificial neural networks. So artificial neural networks is one example of models that can be used to represent the distribution of data. And so from now on, we'll only talk about artificial neural networks. But it's not the only way to have machine learning algorithms, say, to develop machine learning algorithms. So this is very basic. So I apologize for those who know those things already, but this is really very basic notations. What is an artificial neural network? Well, the inspiration is the biological neuron net, where you have, say, neurons and connectors that are the axons, say. And basically what people try to do is to represent input-output functions. So this is another very simple example. Assume that you are just hurting a pin somewhere, or you touch a fire, say. And what you do is you say that instinctively you retract your finger, right? So this is the action. But in fact, this is not an instinct. It is the effect of a biological process. So this information is sent to the nervous system, maybe to the local nervous system. And here there is a model, biological model that operates, and that gives an input, a command, which is a mechanical command to our finger to be retracted, say. So we transform the sensation of pain into a mechanical command, say. So this is the input-output function that you like to simulate by an artificial neural network. So what is an artificial neural network? Is a mathematical approximation of this type of situation. You have input neurons, the yellow ones. You have output neurons, the green ones. And how many you have? Well, it depends on the problem that you want to solve. For instance, again, in the case of the dog, you may have 100 pictures here, photos, and here you just have one neuron with is carrying the value 0, 1. Right? In other cases, you may have different types of neurons. And then you have the internal neurons. Those are internal layers, the blue ones. You may have a single one. In this case, we talk about shallow neural networks, and or many of those. In those cases, we talk about deep neural networks. And every bullet here is representing a mathematical operation, basically. And what you do is to collect the information that are coming from the nearby neurons. Say if you are here, for instance, you collect information from those neurons, and those are real numbers. You multiply by the coefficients, and then you apply a bias. You sum, to multiply your linear combination, you sum a bias, and then you decide to pass this information on or not. And to do that, you can use say a separator. You can decide to stop it, and then it will be a step function, right? 0 or 1, you pass it, or you may use say modifiers in this case. And this function that you have here, which is an approximation of the stepwise function 0 to 1, is called the activation function. Okay. So you take a linear combination, a fine combination, basically, and then you modify it by the activation function, and this information is passed to the next neurons. That's the idea. This is called a multi-layer perceptron because this one is the perceptron. Right? So this neuron here, artificial neuron, is called the perceptron. And again, this is a very long story. This was proposed in 1958 by Rosenblatt. This is the perceptron, and of course you can try to provide also a physical interpretation. You know that there has been the Nobel Prize given to Hopfield, and so you can try to provide a physical interpretation of that. right? So the weights represent the strength of the connection. So you can decide that some neurons are more relevant than others. And they modulate the influence of each input Xj onto the final output. The bias can be interpreted as the activation threshold. Activation threshold means, do I decide to consider this relevant or not? And of course, you just have to take into consideration that there is an opposite sign. So if the weighted sum of the inputs exceeds -b, the neuron fires and returns 1. If the weighted sum is lower than -b, then the neuron remains inactive and returns 0. So this is a threshold that is used here, and the bias allows the neuron to shift its activation bound. Now, when you look at the yesterday, I was talking about the activation, the action potential of a cell, and the action potential of a cell is the way the cell is responding to an electrical solicitation, basically. And you may remember that you have this strange shape. And again, in that case, you can think that B is the shifting on the activation, say, and the height of the picture is dictated by the linear combination of these values here. This is not the very first one. The very first one is from 1943 by McCulloch and Pitt. And in that case, the input were only binary function, binary elements, 0, 1. The output were binary elements. And here there was the activation function, it was the stepwise function. So this is a bit more elaborated, say, than the first one. There's a lot of terminology here that is used in the in this field. A feed-forward neural network is a network like this one. You input a data point, the output is so the points x in Rn, any n, and output is y in Rn, any n. You have capital L layers and the NL number of neurons in the level L. Then you have weights and biases. Weights are described by matrices because they connect different neurons, two indices. Biases are vectors. So this W is the set of weights and biases, and those are called the parameters of the neural network. And then you have activation function sigma, which is a function that goes from Rn to Rn, and these few lines encode basically the feed-forward neural network. So few lines to describe the algorithm. Those are the parameters, as I've said before, but there are also what are called hyperparameters. And the hyperparameters are basically the construction elements of the network. You have the total number of the neurons, so you are just summing up all the neurons that are in the network. You have the number of layers, 1, 2 in this case, and you have the total number of non-null weights and biases. I mean, ideally, or say in principle, there is a complete connection, but in fact, your network in the end will work after the minimization. You will have many of those elements that are put to 0 actually, which means that you are breaking many of those lines. So what is active at the very end after the minimization process is a much reduced number of neurons that are operating. The activation functions. This is the Heaviside function. This is the most used in the computer science environment. It's called the ReLU, rectified linear unit. Sigma of x is the maximum between 0 and x. This is the sigmoid function, and this is the hyperbolic tangent. So many different examples. And I have to say that at least in my practice, the sensitivity of the final result to the choice of the activation function is not that high. So the scheme in general is relatively robust with respect to the choice of the activation function. Even though mathematically speaking, since then we're going to take derivatives because we want to compute we have to minimize functionals. you might be more comfortable in using functions that are continuous. Let's see, let's say. But the actual response of the network is not that changing, actually. So the computer scientists use two different words here when they have to identify a specific neural network. They talk about architecture and expressivity. The architecture is, as you can understand, the way you organize your network, right? So it's the number of neurons, the number of layers, and the total number of non-null weights and biases. And these are regulated by the so-called hyperparameters. The expressivity of a machine learning model is actually the ability of the model to represent complex functions, and is measured by the approximation error. And this is governed by the actual parameters. So the hyperparameters are those that are behind the definition of architecture. The parameters are those that provide the expressivity of the neural network, this capability of generalization, say. There are some further definitions or further elements that will be useful when you try to provide an error estimate or some error estimate. The first one is called the model capacity. What is the model capacity? Is the flexibility of the model to fit diverse data. And basically is an indirect measure of the richness of the hypothesis space. You remember the hypothesis space is the one where you're actually looking for your model function. For instance, if you use a polynomial fitting as a model, the capacity will increase with the polynomial degree. If you use an artificial neural network, the capacity will increase with the number of neurons. So you know that you can operate on this element, the number of neurons, in order to increase the possibility, capability of the model to feed diverse data. This capacity here is basically driven by the hyperparameters. The hyperparameters are those that are behind the architecture of the neural network. Of course, in classification, this is very important because if you have a distribution of data like the one that you see on these three pictures, where you have blue data and yellow data, say, blue data are associated with, I don't know, positive value of a given function, say, and the red, the yellow data are associated with negative function, you know that the model can be chosen in a very, very good way because you can easily make errors that you can call underfitting or overfitting. What is underfitting? Underfitting means that basically you are using a model, in this case a linear model, which is not rich enough to follow the distribution of the data. In overfitting, you use a model which is very good in following the distribution of the data, but too good. So you are using, so you are trying to catch all possible details, even if there is a noise in the data, which is very often the case. And you spend too much time in the training phase, but then you'll not be able to generalize to other cases. So that's too rich, basically. So the good compromise is difficult to achieve, and this will be in that case an optimal fitting. And here is a way where you can see how this generalization error behaves when the capacity is increasing. You do not have to go to the limit. I mean, you cannot increase the capacity without any upper limit. There is an optimal way. Say there's an optimal value of the capacity in order to achieve the best possible generalization. So as you see, this is really depends on the distribution of data and I would say on the process which is behind the distribution of data. So this is the capacity, which is a measure of the richness of the hypothesis space. As I was saying, if you have overfitting, when the network performs very, very well on the given data, but cannot generalize to new data. The fitting process has focused too heavily on the unimportant and unrepresentative noise in the given data. This is where we get the overfitting. And to combat the overfitting, there are some heuristical strategies. The first one, which is perhaps actually is the one that we use, is to take all the data that are available in the training set, say all the data that are available and splitting them into two subsets. One is the training set that is used to find the weight, and the second one is test data. You want to use those data to test the quality of your models. So you have training data, testing data, and in the end you also have validation data, where you have new experiences that were not foreseen in the original set of data, and you want to measure your error. So typically you have three different kinds of data: training and testing that are, say, partition of the original set of data that was available, and validation data that are those that you can acquire later on. So you have 100 further pictures of dogs or cats, whatever, that are not comprising the original set, and use them to test your algorithms, your machine algorithm. So the overfitting corresponds to a situation where the optimization process, which is the one that selected parameter W, is driving down this loss function of the training data, but the loss function on the test data is no longer decreasing. So you have a situation like this one. Okay. It goes, I mean, your loss function is going to zero, but if you look at the test, which is carried out on the new data, you see that there is a limit here, and then from that point on, you will have an increase. So this is a typical situation that you encounter when you have overfitting. And this is a very classical, I would say, certain piège, since you have it very often. Okay, this is to see that machine learning is not the optimization. It's not an optimization problem, because the optimization looks for the minimizer of a function. Like here, you look for the minimizer of a function, but the goal is to minimize another function. So we're just focusing on an approximation of what you would like actually to minimize. There is another element besides the capacity, and it's this BC dimension. From the name of those who proposed this term. And this is, you see a number that you associate with your hypothesis space. And this is the cardinality of the largest set of points that can be shattered by age. What does it mean in practice? I mean, this is a very simple example. Assume that you have a linear model in 2D. You have a binary classification, you have points, you see, you have in 2D, you have a distribution of points, and you have points of class A, the black points, which correspond to a given, positive value of a given function. So assume that you have a function behind your process, and you can take positive values from negative values. So the positive values are carried out by the points that are black, and the negative values by the points that are white. Can you separate these 2 points, right? And which is the model that can separate these points? So if you are in this situation here, you see that a linear model can separate the points from white to black. Okay. But if you have 4 points instead of 3, a linear model is no longer enough. Here it is enough, here is not enough. Okay. So you say that 3 number of points is the capacity in this case, in this specific case. So it's a measure of the richness of the space age, basically. And then the some of the available estimates depend on these 2 elements, the DH. So the capacity of the mesh, and and N, which is the cardinality of the training set. How many elements do you have in the training set? So heuristically, is it a good idea to increase the number of elements in the training set? Intuitively, yes, because you see that the more data we have, the better, right? But you have to be a bit careful. So, for instance, This result states that the supremum between R of F, which is the expected risk, minus RSN of F. Here we're not taking into consideration the optimization error, but we're taking into consideration the fact that we are approximating our, say, integral by numerical approximation using the training set. Well, this is bounded by this expression here. Okay? And what is eta? Well, talking that with probability at least 1 minus eta, we have this. So the smaller eta, the better. So if it is equal to 0, probability 1, we have this error here. So how can we judge this inequality? If you fix the capacity and let n go to infinity, this is fine. This goes to 0. So for a given capacity, given capacity is the possibility of separating leg from my point, right? If you let n go to infinity, so you increase the data set, this is fine. Take this to 0. If we fix the number of training data and we increase the capacity, that's not a good idea. This will go to infinity. So this means that our model has a bad generalization properties. It can perform very well on training data, but not on new data. So the good compromise is to have more or less n and dh that increase with the same rate for the best possible performance. Of course, this is good, but you don't want to go to infinity with the number of data, but this require very extensive computations. So this is the best compromise, having the capacity and the n and the cardinality that increase with the same pace, with the same rate. This is an approximation result for shallow neural network. Shallow neural network is a neural network with a single layer of neurons. Right? So you have input, output, and a single layer of internal neurons. I collected actually different theorems from different authors, but tried to give a synthetic expression of the result. The result, technically speaking, is much more involved, but we wanted to give an idea of the way it behaves. So what is that telling us? We say that if epsilon is a given tolerance, so epsilon is small, and sigma, which is the activation function, is a smooth function. So shouldn't we take the arc tangent? Just make an example. Then for every epsilon and for every f is the ideal mode, say, in the summary space WSP, there exists a neural network, meaning a distribution of weights and biases, right? With N1 hidden neurons, 1, 2, 3, 4, N1 hidden neurons, right? Such that the error on F is lower than epsilon. With N1, so it's an estimate of N1. How many neurons do you need to have this type of error? And you have both the lower bound and an upper bound. And the upper bound is 1 over epsilon to the power d over s, where d is the input dimension, and s is the smoothness. So that's a good sum, right? The smoother, the better. Of course, talking about a process that you don't even know if it does exist, right? Assume that there is a process behind the distribution of data that has this type of smoothness, and here you have d to the same basis to the power d minus 1 over s. So how do we interpret this? The larger the number N1 of hidden neurons, the smaller epsilon. Good, right? If you increase the number of neurons, you have potentially a better error. But if you fix epsilon, so fix the tolerance, the accuracy, then the higher the regularity S of F, the lower the number of N1 of hidden neurons. Again, good news, like in finite elements. The higher the regularity, the smaller number of elements actually you need to achieve a certain accuracy. But the larger the input dimension D, the larger the number of neurons. So if we're working in a high dimensional space of data, then you need a larger number of neurons. So this is the course of dimensionality. You cannot escape the course of dimensionality. But the dimensionality of the distribution of data is very high. So this is for shallow neural networks. So networks that have a single layer of neurons. Now, in principle, if you go from shallow neural network to deep neural networks, namely you allow having many more layers of neurons, the situation should in principle improve, right? So that's another result. In this case, you try to have an estimation of the number of layers, number of neurons, and number of non-null parameters. You know, the parameters are those that connect all the possible neurons. So if all the neurons are connected, it's a dense problem. So otherwise it's a sparse problem. So what you have in this case, if you take the ReLU function, remember the ReLU function is the max between 0 and x, right? So it's just C0, it's not even C. The ReLU function, then you say that for every epsilon, this is the accuracy, there exists an architecture. So you don't know which one. You know, there exists one such that say the error in WSP is less than epsilon, is the approximation error. And here you have an estimate of the hyperparameters of your network. How big should it be? N is the number of layers and is bounded by this quantity here. Then we'll try to end up with a kind of synthetic conclusion. You have an estimate of the number of neurons. Please note that here you have this wiggle, which means that this is true up to a constant that you cannot estimate, of course, like in finite elements, unless you go to the posterior estimate. And then you have also an estimate for the number of non-null parameters that you should play with. So what is the moral conclusion that you can, of course, you can go through the estimate, but the moral conclusion is this one. In principle, deep neural network, those that use many more, say, internal neurons, can represent some functions that shallow neural network cannot represent. So if we have functions that are particularly complex, complex in the sense that their behavior is complex, right? Is more likely that with a deep neural network we'll be able to approximate them better than shallow neural. Deep neural networks typically are more efficient in the sense that they require a lower number of non-null parameters. With the same number of parameters, deep neural network can represent more complex functions than shallow neural network do. So in general, it pays off going to deep neural network. And actually, as probably you know, or some of you know, one of the reasons behind the recent success of artificial intelligence funding, well, I would say that there are two milestones. Actually. One is the discovery of convolutional neural networks, and the cours is behind this, right? Because this was the way to provide a better representation of images, like never happened before. This was one big milestone. And the other one is me. In 2017, the transform. Transform is the algorithm that is behind large language models, those that are behind, for instance, ChatGPT and other generative AI. And both are using actually deep neural network. So this piece of math is just there to say that it makes sense to use a deep neural network ideally or asymptotically, say, to have the better possibility of representing functions of distribution data that are more complex. But then, of course, you have to choose them properly, and this is a different story. Another result is this one. It's say, maybe you can concentrate on this. If f is a function that is in WK infinity, with a norm bounded, and that's in between 0 and 1, you have an estimate of the total number of n is the total number of non-null parameters. So it gives you the density or the connectivity of the network. and you have an estimate in terms of the accuracy that you like to have, and the other elements that you find here basically. So it's a way to provide an upper bound and a lower bound of the. So if we have got the log here, you see that here you have the same exponent, and this divided by 2, and S is any you see number between 0 and 1, and N is a natural number, and is the number of basically of elements that you have in the training set. So those are asymptotic estimates that are there to basically tell us two different things. The first one is that there is a hope that actually it's more than a hope. Neural networks can actually well represent complex functions. So it's like using subspaces of finite elements, or let's say polynomial functions. So you can actually see can actually interpret, at least when you use the real function from the activation function, you can actually interpret a shallow neural network as a special kind of linear finite elements. So there is an intrinsic capability of those subspaces to represent complex distribution of data. And the second point is that you have estimate on the hyperparameters, so on the way you can actually set up your architecture of the neural network, even though, again, all those estimates are up to a constant that is hard to quantify. But at least you go to the early phase of finite element theory, we are not that far from here, right? I mean, the type of estimate that you had at that time was about the same kind. Okay. Of course, the devil is in the detail, and then you need to train your networks, and you need to optimize, and you need to find the minimum of your loss function. And here, usually, in my personal experience, it's a hard topic. So when you train, you are actually using a performance measure, and you want to find the parameters that minimize this loss function, basically. And therefore, you need minimization algorithms. Now, we are typically working in a very high dimensional spaces, especially if you use deep neural network, we have many parameters. So we're working in very high dimensional spaces, and those functions are not convex. So there's not a single minimum. Yeah. So there are many local minimum. And if you have experience with minimization, you know that it is a very hard topic. I mean, find algorithms that work for minimization of functions that are non-convex. So how many, I mean, which kind of algorithm can you use? Well, different kind of algorithm. The most classical one is the gradient descent. You want to move along the direction of where you have the steepest descent. So this is called the gradient method. Basically, you are at a specific point, xk, and you want to go to the next point, xk plus 1, and you want to convert to the minimum. And then you write sk plus 1 as xk plus alpha gradient minus alpha gradient of your loss function, the point xk. That's why we call it gradient method. Basically, the classical approach, say. Otherwise, you can use the stochastic gradient descent method. I will mention it, and many variants. And I think what in my group actually they use this is mostly the Adam or the AdaGrad. I'll give you the formula in a while. AdaGrad is adaptive gradient, where you change the rate alpha that you put in front of the gradient, or the so-called adaptive moment estimation. So Adam is not the name of the person; it's just an acronym of the name. So this is a typical situation, right? You have a map like this one, unless you are not in R2, you are in Rn, and then maybe very large. And this is the gradient, the standard gradient descent method, one that we teach to, so say, first year students, second year students, first year numerical exposures. So you start from a given set of parameters, and remember the W contains both the coefficient capital W that connect the different units and the biases. So you start from a given guess, and then at every step you work, you update your WK in this way. You take WK minus theta K times the gradient of L, the loss function at WK, say. Most often, function is non-convex, it's already non-convex. So the gradient descent method can convert to local minima and not to the global minima. So this that's a word. Eta K is called the learning parameter. This one. So you can take it constant over a long iteration, or you can adapt it. You can take it adaptively, and in that case, it should go to 0 when K goes to infinity. And here, of course, you may make a mistake. So if it's too small, you stay too much on a branch before converging to the minimum. If you take it too large, you may oscillate. Again, this is a representation in 1D, but then you have to think of a very high-dimensional stuff here. The stochastic, when n is very large, n is the number of, say, the training set, the computation can be very expensive because you have to take the gradient with respect to all components, say. An alternative is to replace the mean of the individual gradients over all training points by the gradient of a single randomly chosen training point, or the mean of the gradients on a randomly chosen subset of training points, and this is called the mini-batch. So instead of computing all these gradients, you just take one representative. So if you look at the algorithm before, you have a given set of parameters that you take for granted at the beginning, and then you update it. But here you take not the old gradient, but just the gradient at a randomly selected component. Okay, another possibility is to shuffle all the integers into a new order, and then here consider just one component. Of course, the point is how you choose the learning rate. And here you have some, say, recipes, and this is experimental, but it works reasonably well. It's eta K is given by beta divided by gamma plus K. So basically, it is like the inverse of the iteration, so it goes to 0 in the end, and beta gamma again should be chosen experimental. So. You have results that compare the gradient descent behavior of the, say, of the iterative error with the stochastic gradient descent iterative error. So in the case where you're using the stochastic gradient descent, you have the average between L of WK minus L of W star. W star is the ideal set of parameters, the one that characterize the that are associated with the loss, the absolute minimum behaves like 1 over K. And the lesson to learn is that if n is large, if the number of training set is very large, the SGD, the stochastic descent, gradient descent, is computationally speaking more convenient than the gradient descent. That's why we typically use the stochastic gradient descent.
Independent of L.
Yeah. You can go beyond the SGD to try to mitigate the dependence on the estimate of the gradient, which may be very noisy. And this is because basically the activation function can undergo what is called saturation, can produce very small derivatives that reduce the size of the gradient update. So we're not updating the gradient anymore. If the convergence, the iteration anymore, if the gradient goes to zero. So this is there are algorithms that allow to do that. So you move from the stochastic gradient descent method to either second order method. You know, gradient is a first order method. You just use the gradient. You could use the Hessian to modify your points, right? And another term depends on the Hessian, which is second order method. So this is one way, and the other way is to move in this direction, to use the batch gradient method, putting not a single component of the gradient, but putting some components, a lower number of components that are chosen stochastically, and then you go to the second order method. In that case, you have batch Newton method, but this will be the stochastic Newton method. So this is the idea, to move towards second order methods and not just stick with first order methods. This is stochastic descent. Well, these are algorithms, the way you modify the algorithms for this, and these are the second order method. And the point is that the choice for second order method on the learning rate is a big issue. How you modify the eta k in front of the gradient for second order method is not an easy task. The alternative is to go to gradient descent with momentum. So each step is chosen as a combination of the steepest descent direction and the most recent iterative displacement. So you are just modifying the gradient method by adding this term here, which accounts for the difference between, say, for the last increment, again, with a constant that you have to measure. This is a moving parameter, it's called the momentum parameter. And this is improving with respect to the previous situation. And the last algorithm, which is the one that we're actually using, is Adam. You use first order gradient-based optimization of stochastic loss function. You use an adaptive learning rate for different parameters, and it's computationally efficient. It has very little memory requirement, and several other nice properties. And this is actually what we use. So this is the other method. It was proposed in this paper. You see, compute the gradient, you use the first order model, use the second order model, and then you update the coefficients, and you select the adaptive learning rate in this way. So again, you have parameters that you have to tune, and here are numbers that in general work quite well, independently of the programs. So the issue of the message, the take-home message is that minimization is a big issue here, especially when you have very high dimensions, and finding the good minimization algorithm is really extremely important. This backpropagation stuff is a relatively simple-minded idea, but it was absolutely fundamental in this business, and this was proposed several years ago. And it's a way to compute efficiently the gradient in a recursive manner. As you have seen, you calculate many times the gradient, and the gradient is the gradient of a function that depends on very many parameters. So this computation is very hard, but you can do it in a reverse order, starting from the last set of neuron to the first set of neuron. And this is called the backpropagation, and it's a kind of, actually it is an explicit formula that you can use to compute the gradient in an iterative way. I mean, if you are aware of using standard gradient method or Richardson method in numerical linear algebra, you know that you can, by a recursive formula, you can compute basically at every iteration the new values of the coefficients, for instance, in terms of the previous one, by very simple algebraic operations. So this idea is very clever. I mean, in the end is obvious, but it was not obvious at the beginning, and is a way to compute efficiently the derivatives of the loss function with respect to the parameters, to the weights, and to the biases in a very efficient way. So this is called the backpropagation algorithm, and I think it's a masterpiece in the evolution of neural networks. Training, and I think I'm about to end. Well, in general, you should train your algorithm by choosing the parameters, but in fact, you also have hyperparameters. So here there are two ways. The hyperparameters are those that dictate the architecture of the neural network, the construction, right? So in principle, you can choose them and fix them, right? Fix the architecture. And then you take into consideration only the parameters and minimize the parameter. In fact, it's useful also to try to optimize with respect to the hyperparameters. And this is typically what we do in a first step. We basically update the parameters, and then in a second step, we update the hyperparameters. So it's a kind of how to say nested operation, nested minimization, where you take into consideration the contribution of the two things. How to choose the loss function? Well, this is the discrepancy. If you can have a regularization curve. Again, here is a lot of freedom. You can have a thick enough regularization where you basically add the Euclidean norm of the error, or you just use the L1 norm of the error. So this is another way you can set up your architecture, and this is the choice of the hyperparameters. Again, you can do it manually, or you can do it with a nested minimization. The last part, but I'll not go through because it's very technical, but you'll find it in the notes if you are interested, is the way you can set up deep neural networks, convolutional neural networks, and other neural networks that have been used for, as you see here, fully connected layers, convolutional layers, pooling, attention layers that are those that are behind the ChatGPT, or say, the generative AI models. And you see that you go much beyond the original idea of the perceptrons in identifying spatial structure of the neural networks that are suitable to address specific problems. Last but not least, but I'll say nothing about this. If you have been involved with any experience with neural network computation, you know that GPUs are very important here to solve efficiently the minimization algorithms. GPUs rather than CPUs, and actually this explosive value of NVIDIA in the market is really dictated by the fact that, especially with generative AI, you need to say minimize over a huge amount of parameters, and GPU architecture are working very well. And here is just a remark on the way GPU architecture work. Attention models are behind the generative AI models, and this one as well. So this is, and those are the computational challenges. And here you see the way you may recognize some of these names that are behind the model development of generative models like BERT, GPT, and so on and so forth. And here you see the cost for the training set of neural expressive and about 24 operations. This is really something that is shocking somehow, because it tells you that this evolution is not sustainable if it is not mitigated by new algorithms or by new computers, or by, I don't know, changing somehow the kind of task that you want to face. All right, I will stop here. It's 30 sharp. Oh, yeah.
Okay, thanks a lot, Alfio, for this wonderful and very clear presentation. Questions? Let me ask one, maybe online. If you have questions, do not hesitate. So I am a little bit astonished about the approximation result that you have. Something I don't understand, and you will certainly clarify this. In finite element, we know that the regularity, of course, is important for the approximation, but we don't use all the regularity. Here, you seem to use all the regularity. So I somehow understood a little bit.
Is this?
Voilà, so it's this the slide here. So here, S, it can be any. Okay.
S is, yeah, this is,
Yeah.
okay, I see what you say.
Okay,
So
so,
in
sigma here is infinity, so maybe it's related to this, but on the next, so it's already astonishing for me that you can use all the regularity of the function you want to approximate, but on the next slide, when you have a deep network, and you sigma is ReLU, so ReLU for me would be
Yeah,
like
it's not smooth.
one element. I don't understand why you can use again all the regularity of the function. Is there something you can? So I believe that the theorem are true, but I don't understand why.
That's the point.
Okay.
Okay. Oh, no, I cannot answer. I mean, you should look at the proof and see how it works.
Okay.
Well, the real function is. It's true that the real function is not regular, right? But the real function is only there to basically to filter the amount of information that we have to pass on, right? But if you increase the number of, I mean, even if you have even if you have an activation function which is not small, but you increase the number of layers, you are increasing the potential of your approximation subspace, basically. So it's not necessarily a contradiction, I would say, because sigma is only part of the story. Right?
Yeah, of course. Yeah.
Yeah. But I cannot give you any more specific answer because this should require going into the.
And for deep, where enters the number of layers? Does it enter somewhere? Is L the number of layers?
L is the number of layers, yes.
Okay.
L is the number of layers, and then it's the number of neurons.
Okay. So if you understand the.
So if you fix for a given function, say with a given regularity, if you fix the accuracy, here you have the indication about the architecture. So the size of your neural network, basically, in terms of number of layers, number of neurons, and number of non-null parameters. So how many connections do you have between the different neurons?
Yeah, question is this. You have room to build the neural network? Rules. So
No, you don't.
Just a theorem.
Yeah. This is a general, yeah. Okay. If you know, when you teach the Weierstrass theorem to our first year calculus, right? We say that for any continuous function, there exists for every epsilon and every continuous function, there exists a polynomial of degree n such that the error is less than epsilon. You don't know what is n, and you don't know how to construct it, right? So it's an approximation result without any constructed factor. And here is the same, but this gives you an idea of the size of the problem. But then this is very problem dependent. For instance, the convolutional neural network that you use for images are very different than the neural network that you use for text, for the ChatGPT, for instance, right? Or for other applications. So the construction is really very much dependent on your target, on your problem. So this is an indication about the size. But then, again, you don't have C here, you don't have constants here, right? It's just an asymptotic indication. But it's a very heuristic kind of thing. It's a very, I mean, my knowledge, very. On the other side, even if you take finite elements, even though you are putting everything on a much solid mathematical ground, right? You know that when you change the problem, you go from the heat equation to nonlinear elasticity, you know that the performance is very different, actually, even though the guidelines are the same. You have a question, Lee?
Yeah, because here when you look at the equivalent of the number of neurons and number of parameters, they scale the same way. So does it suggest that in fact the picture is not really the one on the bottom right, but it's not a fully connected network, but.
Oh, no, yeah, sure.
And
So, okay, that's a very good point. Here I'm representing a generic, fully connected. But then, in fact, what is important is to see how many of those connections are actually activated, right? And this is what actually finding you.
And is it something that I mean, it's true in general, and also that can be used in the optimization algorithm that are designed. So I think you can see this by
Well, actually, the optimization algorithm is the one that in the very end will give you the value of the parameters. And many of them will be zero. But this is something that you find a posteriori, unless you enforce them a priori. I mean, you can do it by design, but typically you start from a fully connected and then you let your algorithm go and to find the values of the parameters. So you end up with something which is not fully connected.
Other question? If not, thank you again, Alfio.
Yeah.